Recording will start now.
Good. I don't know if you want to make a backup save as usual. Okay, so let's get started for today's session. So today we have a thematic session about the interplay between probability theory and Coccidir groups. So two disjoint talks at this intersection. The first one is by Russel Lyons from Indiana University, and he will explain us why monotonicity is special for random walks and groups. So we are listening to you. Thanks.
Thank you, Sebastian and Bastien. Thanks very much for inviting me, and to everyone for coming. Right, so the title is longer than what I have on my slide because it was a long title. Just wouldn't all fit here. And this is joint work with my former postdoc, Graham White. I encourage you to interrupt at any time with questions. And in fact, several times during my talk, I will ask you to answer my questions. So please do, I try to make it interactive. If you show your faces, it helps me see better how well you're following, but at least I do have a few people already sharing. As far as I'm concerned, you should feel free to share your video, share your faces. Okay. As Sebastian said, Coccidir groups is going to be part of this talk, but I'm not going to mention them for quite a while, actually. But illustrations will, as you will see, come from Coccidir groups. I'm going to start with just a very simple example, which is a regular tree. And in fact, a three-regular tree. And we will think of this as a Cayley diagram of the free product of three copies of Z mod 2. And so the Cayley diagram means that for each edge, it's labeled with the corresponding generator, A, B, or C. So A, B, there are three generators, and the relations are that they're all involution. So this is Z mod 2, okay? And there are no other relations. That's why it's a free product. So there are no cycles. Now, so I just labeled them three colors here. All right. Any questions on what a Cayley diagram is and why this is this is a portion of the Cayley diagram of this group? No. Okay, good. So we want to consider random walks. Let's start with just a discrete time, simple random walk. So at each point, I should have mentioned the vertices are the elements of the group, which I didn't label. And you join two vertices by an edge when you can multiply on the right by one of the generators to go from one to the other. And here, because they're all involutions, if you multiply twice, you just go back to where you started from. So this, like all Cayley graphs, it is homogeneous. It looks the same from every vertex. You could label this one the identity, this one A, this B, this one C. It doesn't matter. So what I want to do is consider the speed of escape. In other words, after many steps, after n steps, it's at some location, which will be at some distance from its starting point. I take the distance, I divide by the time, and I take a limit as the number of steps tends to infinity. So what will be the escape speed for discrete time, simple random walk on the three-regular tree? If you don't want to speak, you could also put an answer in the chat.
One third.
Well, what happens? Oh, someone wanted to say something?
Yeah, yeah.
Oh,
we are several people to suggest 1/3.
Yeah, it's 1/3. Okay, can someone explain why it's 1/3?
2/3 minus 1/3.
Yeah, so every time except at the starting point, you have 2/3 chance to increase the distance by 1, 1/3 chance to decrease the distance by 1. So 2/3 minus 1/3 is 1/3. Exactly. Good. Okay, So now what we're going to do is consider the actual type of random walk that I'm concerned with in this talk, which is continuous time random walk. Each edge is crossed at rate 1. So in other words, there's a Poisson process of rate 1 for each edge. And whenever the walker is at a vertex, the first edge to ring that's incident to it is crossed. So in this case, again, just time is continuous, but I do the same thing as before. What is the limiting speed now? All right, Sebastian says 1. And why is it 1?
Because we go 3 times faster.
Exactly. So that's the key thing you have to remember for the minimum of exponential random variables has rate, which is the sum of the rates. So it moves at 3 times faster, but otherwise it does the same thing as discrete time random walk. So 3 times a third is 1. Okay. So there's a simple little warm up. But now let's suppose that the rates on the edges are not all 1, but they depend only on the generator label. So in terms of the colors, every red edge has the same rate, every blue edge has the same rate, every green edge has the same rate. All right. So let's consider the simplest case. They're not all 1, but all of 1 are 1. In other words, 2 of them are 1, except for one of those generators, which has rate rho. All right. So if rho is 1, the speed is 1. What if rho is 0, which means that edge will never be crossed? What is the speed in that case? Zero, right? And it's 0 because wherever you start, there's only a line, z's, given by those 2 generators that you can cross that it will walk on. And so it's like continuous time simple random walk on the integers, which of course is recurrent, has speed 0. Okay. Let's consider another extreme case where rho tends to infinity. What will happen to the speed as rho tends to infinity?
It's 2, no?
Why 2?
Because like at rate 2, we move in the non-rho generator, and anytime we move, we just we make an additional step. So it makes the distance even larger. So it's more than 2. It's what? Yeah, it's 4. Oh, no, okay.
So Adam Timar remarks, it looks like a walk on a 4-grading tree. It sort of looks like that. And okay, but it's actually not so obvious, right? What happens, that edge, which has very high rate, is going to be crossed many, many times until one of the other edges is crossed. And then you'll be incident to a different edge of rate rho, and the same thing will happen. So it's actually complicated. The limit is 5/3. It's not something you're just going to figure out in your head quickly. You could figure it out in your head, but it would take you a bit of time. Okay, nevertheless, we see, so we have 3 data points here for varying rho, 0, 1, and infinity. And we see that it's increasing for these 3 points in rho. So is that a general phenomenon? Is the speed increasing in rho? And by thinking about that case when rho is large, hopefully you've seen that this is actually not so obvious, because what happens when rho increases? That edge, of course, will be more likely to be crossed, but it also happens faster, and it will also be more likely to be crossed and more quickly once you do cross it. In other words, to come back. So it's not really obvious what happens. And hopefully by thinking through these examples, you can see that it's not so clear. That is going to be one of the fundamental questions here. So in this particular case, there's a formula I've written down here for the speed. Well, you can see it's It's not so obvious. Doesn't simplify. And it turns out that this is increasing in rho, but even that is not so obvious with the formula. So is there a good reason that it is increasing? So how can we decide whether we have a good reason? Well, we could answer the following questions. Suppose the three rates are different. Is the speed increasing in each rate separately? What if the degree is larger than 3? What about other calligraphs with symmetric rates on the generator? So the same rate of going one direction as the other direction, okay? If we could answer these questions, if they were yes, then presumably we would have to prove that by having a good reason. We're definitely not going to get a formula in general. All right, so that's some motivating questions. Now, there's one special case which is easy. Whatever the rates are, whatever the group is, if you multiply all the rates by the same factor, then, and the factor is bigger than 1, then the speed will go up. And why is that? I see people nodding their heads. Why is that?
Just reparameterize time? We'll just, yeah.
It's the same thing as just if you increase the rates, decreasing time, same thing happens faster. So the speed will be multiplied by that factor. So that's the simple case, right?
Can I ask a question?
Yes, in fact, I was just going to ask if anyone had questions.
Okay, because there is this red box with questions inside. I had a variation of it, and I wanted to know if the question is interesting or not. If we take a tree, and instead of having like one rate per color in the previous tree, we just have one rate per edge, but it could be like infinitely many, like each edge has its special rate, not in a periodic manner. And is this monotonicity question interesting or not? Or like, is there something to say about this question?
Yes, so you're right. That is, of course, one of the first types of questions to look at. But it's actually not so hard to get counterexamples there. Again, it's not so obvious that they exist, but it's much easier because, of course, you have much more flexibility rather than working in a context of rates on calligraphs where the rates only depend on the generators. So, there are some subtle things that happen. I'm not going to talk about that more general case.
Okay.
So I have.
Thank you.
I don't think I have anything particularly interesting to say about that general case. There are counterexamples. Although there's one case, if you just consider that a single ray, we do treat in our paper also. I'm not going to talk about that here. And there you have, each edge has its own rate. Any other questions?
If I may, in the case of a 4 regular tree, in the case of a 4 regular tree, you would get different questions depending on how you write it as a calligraph, whether it's a calligraph of Z mod 2, and you take the free product of 4 copies, or if you look at it as a calligraph of a free group.
Right.
The question will be different, right?
It could be different, that's correct. So it could be different, that's correct. So the case, I hear an echo. Someone has I hear an echo. Something second sounds source. So yes, if you think of the free group on 2 generators, then there are only 2 possible rates. But that's the same as having 4 copies of Z mod 2, where we fix 2 of the rates to be the same and 2 of the other rates to be the same. So it would be more special. But so if you have a positive answer for the 4 generators, then that implies a positive answer for 2 generators. But that certainly falls in this other category of other calligraphs. It wouldn't just be a product of Z mod 2. Anything else?
Sure. Thanks.
Anything else?
This A squared is the identity. Seems to be related to reversibility. Are you going to concentrate on reversible things?
Yes, correct. Yes, rates are symmetric. Yeah, otherwise things can be quite different. Okay, so here's an example, or going to lead to an example of another Cayley graph besides free groups. What is this? Well, it came from the OWPS logo on the website, and given by a portion of it and reflected. So it's this. So there's a little triangle here, okay? Angles pi over 2, pi over 3, and pi over 7 in the hyperbolic disk. And I consider a little triangle portion of that logo, and it's just reflected in the sides, okay? And that's where that picture came from. So it's a reflection group applied to a certain triangle portion of the logo. And here's the Cayley graph of that group. So it has 3 generators, there's reflections in 3 sides. And there are 3 generators, 3 relations, AB squared, so that's like A, B, A, B. So you go around a rectangle. BC cubed, B, C, B, C. Oh, sorry, B, C, B, C, B, C. So it's a hexagon, and then CA to the 7th, so it's a 14-gon. So it turns out that the Cayley graph is a dual of the tessellation by triangles. So the white lines are just give you the triangles or the sides into which we're reflecting. These are geodesics in the hyperbolic disk. But the Cayley diagram are the colored edges, the blue, red, and brown. And so that would be another example of a Cayley graph where definitely, even with rate 1, all with rate 1, no one knows the speed. There may not be a nice formula, but this would be another example where we would ask these questions, okay? All right, so there are 2 themes in this talk. One of them is the speed on these infinite graphs, infinite Cayley graphs. Another one is about finite Cayley graphs. So of course, there's no question about speed at 0, but there's something else to ask. We're gonna consider the same type of continuous time we're gonna walk. Now, as time tends to infinity, the distribution tends to the stationary distribution. And what is the stationary distribution?
Uniform.
It's uniform. Everything looks the same everywhere. In fact, even if it were not a Cayley graph and the rates were arbitrary, the stationary distribution would still be uniform because this is this particular type of continuous time random walk, but that doesn't matter. Okay, so Yiping Hu, after seeing our results on speed, asked us this question. In this finite case, does increasing a generator rate decrease the distance to the stationary distribution at any fixed time? Okay, fixed time, not at asymptotic. That seems plausible that it would, right? So here's an example. This was on my title slide. Again, using the logo, but this time it's on a sphere. So it's this reflection group. Again, I take a triangle, angles pi over 2, pi over 3, and pi over 5. And reflect it around. There are only finitely many triangles and get that tessellation. So here's the Cayley graph, again, with the 3 generators. So the presentation, it looks very much like before. The relations are the same, except we have the power 5 instead of the power 7 to go around this 10-gon. And here's a nice picture from Wikimedia of this same Cayley graph without the coloring of the edges. So you can see all the way around the sphere. Beautiful picture. So, right, all the elementary cycles are given by these generators. Of course, you can put them together to get bigger cycles, but that's where all these faces come from. So are there any questions on the understanding of this as a Cayley graph?
Why this group is finite? With these relations, This is a finite group.
Well, of course, it has to be proved that it's finite if you give this presentation. But it is true that if you have a certain size of this triangle, then it will exactly tessellate the sphere. And so therefore the group will have to be finite. Not sure if that answers the
But
question.
in the previous example, you have again three relations, but the group was infinite.
That's right. So first of all, it's if you just are given a presentation of a group, it's impossible to say whether it's going to be finite, infinite, or even trivial. The word problem is unsolvable algorithmically. So I can't give you a general answer for why a group will be finite or infinite if you just give me a presentation.
So the only difference between this group and the previous group is the exponent 5 being
Correct.
7.
Oh.
Yes.
No? In terms of presentation, I mean. Yeah.
That's right.
Thank you.
And so you should think about it in terms of these reflections, the reflections in these triangles. So it's a particularly geometrically inspired group. Of course, you have to check everything I say, which I'm not doing, all the group theory. I'm just stating these as facts. Okay, so those are two themes now. Let me return to the first, which I'm going to spend most of my talk on because I won't have time to deal much with the second. So remember, we wanted to see whether the speed was monotone in the rates and if there was a good reason. So one good reason would be if the following question had a positive answer. Like consider two random walks. For one of them, the rates are all higher or at least as much as the first one. Can we couple these two random walks so that the more active one, the one with higher rates, is always at least as far from the initial position as the other one? If we could do that, I think we would feel that we understood why the speed was at least as much, right? Why the speed was monotone. So to talk about this question, let's introduce a notation. For each generator S, let's call little r sub s the rate corresponding to that generator. So it turns out that this coupling question does not have a positive answer, even in the simplest cases. We're going to start with the simplest, one of the simplest cases, our initial three regular tree, and the rates on generators B and C are both 0. That means it only moves across back and forth across some A edge, depending on where it starts. Let's say it starts at the identity. Okay, moves back and forth between the identity and A. So I claim it's not possible to have such a coupling in that case. Now you might say that's too trivial. But in fact, even if all three rates are positive, there's still no such coupling. So let me prove that to you. So do the first case first. So let's say the first one has rate 1 on edge A and the second has rate 100 on edge A. The other says 0. Now, intuitively, right, the one at rate 100 has got to go back and forth many, many times. And the one at rate 1 is just going to go, moderately back and forth. How is the fast one going to stay at least as far as the slow one? It can't, right? So to prove it rigorously, let's look at the following example. The first process, this moderate one, has a good chance of staying at the initial vertex until sometime between 0.4 and 0.6. We're only looking at the first unit of time. And then it will stay there until time 1. Reasonable chance of that happening. But the more active one is unlikely to take a path, very unlikely to take a path that moves farther from the starting vertex. In this case, why? Well, that would require staying at this other vertex, the non-starting point, at all times between 0.6 and 0.1. That's extremely unlikely for such an active walk. Okay. So it's impossible to couple them. Doesn't matter whether it's Markov coupling or not. Any questions on that? Oh, so there was a question in the chat about lazy version. So this is continuous time, and laziness is built into the fact that it's continuous time. Oh yeah, someone else answered that. Okay. just the delays things. RB and RC in this case are 0. We're doing the first case first. They're 0. Any other questions? Okay, so now let's prove that the general case is also not possible. Now, when I say in general, I don't mean it's impossible for all choices. I just mean in general, it's impossible. So suppose RB and RC are both positive. Now choose a time which is really small. When I say choose a time which is really small, in effect, that's going to make RB and RC very, very close to 0 from the point of view of that time. Unlikely that anything will happen by that time. Now I'm going to make 2 choices for R sub A. Smaller one is 1 over t. So it's like the first unit of time, RA was 1. And then the second one will be 100 times larger. So it's essentially the same as the proof in the first case, because it's very unlikely that anything will happen on B and C. Okay, so there were some questions about finiteness. Jason answers, okay, good. If you add a probability, probably a further part grows. I'm not sure what the question means. You add a probability. Okay, so in fact, it turns out that there are counterexamples to monotonicity as a general phenomenon. Here's a case which is very much like a tree, but instead of a vertex, for each vertex you have a 10-gon, in fact, Z mod 10 with various generators with various rates, and they're connected by edges, so it's a product with Z mod 2, a free product of Z mod 2s with others. This would go out forever. In my slides, if you click on this, there's details at the end if you want to look at that later. But there are counterexamples which are not complicated. I mean, in the sense they're not complicated graphs. Monotonicity does not hold in general, even for relatively simple graphs. And there are like 3 rates, 2 pairs of 3 rates. However, what about the case of trees? Now we started with 3 regular trees there, okay? Here it turns out it is monotone. The escape speed is non-decreasing in each rate separately. Now, how are we going to prove that? And how are we going to give a nice proof, given that we just said that this kind of coupling that we would like is not possible? Well, it turns out we are going to use coupling, but it's just not as nice as that. It won't be as nice as this coupling that works for all time. We have to be very careful. So the key tool is a simple one that will allow us flexibility in our coupling. And in fact, someone asked about laziness. This, in fact, will be introducing some extra laziness, even though in principle we don't need it. So we're going to do the following thing. For each edge with rate R, we're going to use a Poisson clock with rate 2R instead of R. But when this new clock rings, you flip a coin, and with half chance, you move like the original clock would tell you to move, but otherwise you just stay where you are. So you cut down the rate to what it's supposed to be. And I'm going to use capital R, R standing for refresh time, for this Poisson process of twice the rate, right? So I'm going to introduce extra randomness that's going to help us with our flexibility to do our coupling. So to prove our theorem, there's going to be 2 preliminary steps that we will establish. One is, suppose I have 2 adjacent vertices, W and W prime, and W is closer to the initial position, say the identity, than W prime. Claim for all times, the problem, and ZT is our continuous time random walk, the chance that it is at the closer one is at least a chance that it's at the further one. That's step 1. And step 2 will be the following. Suppose T1 is some arbitrary positive time, and S is one of the generators. Now consider the following 2 processes. Z superscript 1 is just our regular random walk. Z2 starts the same way until time T1. Then this refresh ring along the generator S is triggered deterministically. In other words, it's not at random. At that time, we're definitely going to trigger it, which means then you have to flip a coin to decide what happens at that time, okay? And then you just run the random walk with the same rules as before, okay? So this is a very small change. Instead of increasing a generator, we only once increase a ring on generator S at time T1, all right? Now we're going to couple these two processes, Z superscript 1 and Z superscript 2, in the following way. At all times larger than T1, either they're in the same state or the second walk is farther from the origin than the first. Right? That's a good thing if we want to show monotonicity. So it's a small step, sounds like a small step, but this is going to put these together to do what we want. So why is the first step true? So let's say you can get from W to W prime by multiplying by generator A. They were adjacent. So there's some generator, let's say it's A. To prove this, I'm going to give a probability preserving injection from paths up to time T that end at W prime to the paths that end at W. So for any path that ends at W prime, now it has to be, right, since W is closer than W prime to identity, you have to be a W and then cross this edge from W to W prime, right? Which means, and so let's say T, capital T is the first time that this happens, and the ring refresh clock must ring at some time also. Of course, it could be there and leave without the refresh clock ringing, but at some time you must cross, so this R sub A must ring at some time, okay? When it's at W. Let's T be the first time. Now we're going to modify, so this is the coupling. Both these steps are proved by coupling. Well, the second step we're going to do coupling. So this is proved by coupling. We're going to modify the path by just changing that coin flip at that time, capital T. That's all we do. Everything else is unchanged. Every other coin flip. What is the difference to random walks considered before? I'm not quite sure what this question means. These are exactly the same walks that we were talking about before, except we're using, instead of the Russel Lyons with rate little r, we're using big R and coin flips. So they have exactly the same. All right, so that's what we're doing to make this other path. But notice the coin was a fair coin. Probabilities are not changed, and we did not condition on what the coin flip was at time capital T, just as it rings. Okay, it might not have crossed. So if the first one crossed, the second one won't cross at that time. If the first one did not cross, the second one will cross at that time. So if I consider this edge W prime, what happens is one of them goes to the other side and the other one stays on the side where it is. And then they just follow the same generator. So it's like a reflection in that edge. On a tree, reflection is very simple, right? The tree looks the same on both sides of this edge. The generator's over here, corresponding generator's over here. You're doing the same thing. So it's a reflection of the random walk in that edge. In particular, what happens at the end, if it ended at W prime, which is what we're considering, it now ends at W. So this is our probability preserving injection. Why is it an injection? Well, it's actually a probability preserving bijection from the paths that end at W prime to which path? We can say exactly which ones they are. The ones that end at W and were at W at some ring of refresh clock RA. So you can go back and forth just by changing what happens at that time, capital T. And so it's actually a bijection. So that proves step one via coupling. So I think that provides a good understanding for this inequality. Now step two, where we want to make something happen for all times after time T1, where you have this extra refresh ring. I don't have time to give the whole proof, but this gives you the main idea. Let's look at this first walk, which is unchanged at time t1. It's somewhere, and the S is a special generator we fixed, okay? So wherever we are, there's an edge labeled S coming off of it. So there's 2 points, gamma and gamma S, and I'm going to label the one gamma, which is closer to identity than gamma S. It doesn't mean it's at gamma. It could be a gamma or it could be a gamma S. But the one I'm going to label gamma is the one that's closer, all right, to identity. So gamma's random. So Z1 and Z2 are going to be coupled. Up to time T1, they're independent, conditioned that Z2 is also in the set gamma gamma S. Well, they have the same distribution up to then, so there's no problem doing that. Okay. Now, at time T1, we need to flip a coin. But instead, it was a fair coin. It was going to decide which of these two things it's going to be in Z2. Instead of flipping the fair coin and deciding move or stay, we're just going to say, well, we could randomize equally among these two because it has a chance half-half. Now, how are we going to decide what to do? This is our coupling. We're going to let it equal gamma S, the further one, if the first one is at gamma S, but sometimes even if the first one is at gamma. And we can do that because at step 1, the chance of being a gamma is at least the chance of being a gamma S. And we need to do half-half, and so we can do that. And that guarantees that at time T1, or just after time T1, after we do this randomization, Z2 is going to be at the same position or at the other edge. And then they're just going to do the same things as before. And that will guarantee that the second one stays further. Okay, I know this takes time to really think through. I don't have time to let you do that right now, but that gives you some idea of how the coupling works. Now, how do these get put together to prove our theorem? Okay, so here's the theorem again. So we're going to show that the expected distance at time t is non-decreasing in, say, rate RA for every time. Now, if I increase RA, remember, we're going to do that by using these refresh clocks. So that just results in extra rings of the refresh clock corresponding to generator A. And up to time t, there'll be some finite random number of them, also distributed. So let xt be our original random walk. It was zt before, but now I'm counting, have two versions, so I'm going to call it xt. And yt be the one where RA has been increased, okay? And I want to say that this for x is the most this for y. So I'm going to couple x and y. They're going to have the same refresh clock rings at the same times, except that y has some extra number of rings up to time t. I'll call that extra number of RA, n sub t. Okay. Now, when
Sorry, can't you remind for what process you have no monotonicity? You start from the process with no monotonicity, and this one you have monotonicity. Yeah? The first theorem was about the absence of monotonicity. Yes?
I said there's a counter. Okay.
What's the difference?
I said the first thing I said was the coupling. The best coupling is impossible, even for the 3 regular tree. Second thing I said was that there are counterexamples. It was Z mod 10 star Z mod 2, for which there's no monotonicity. Here I'm
Can you return to the formulation of the first
and there is
theorem?
monotonicity.
First theorem, not about non-monotonicity.
Excuse me?
There was such theorem.
Yes, Z mod 10 star Z mod 2. With certain
In your lecture, the first theorem was the absence of monotonicity, yes? Or no?
The first thing was absence of coupling. The second thing was absence of monotonicity. And
But what is the difference between situations?
Yeah, different, of course. And the third thing is there is monotonicity. That's what I'm proving now.
Can you formulate again the theory about absence of monotonicity? Absence of monotonicity.
This was the
Yes.
counterexample to monotonicity.
What is this? There was a process.
It's a continuous time random walk with the
What
rates
is the
of
process? What's the definition of the process?
There are certain rates on the generators. There are 3 generators, one corresponding to blue, one corresponding to brown, and one corresponding to red. And there's 2 sets, one bigger than the other. And you find for the bigger set, the speed will be smaller. And if you go to my slides and click on the details, you will find precisely what those rates are. And a proof.
Can you repeat the formulations of the group, the definition of the group or the graph?
The group?
This is example. What is the theory about it?
This
What
is
was the
zero.
theory about the absence of monotonicity? Can you formulate it again? This was in the text. Yes.
There's
The theory about the absence of monotonicity. I understand that. What is the difference between your new theorem and the first theorem?
It's a different
Why
group.
for the first theorem was no monotonicity, and now you have monotonicity? Huh?
Yes, it's a different group. That's the difference.
Okay,
Different
maybe we
different
can keep this for questions in the end and resume to what you were saying. As for the group, I've written it in the chat if this was the question. So it's Z-mod 10 free product with Z-mod 2.
Yes.
But okay, maybe we can go back to.
Right. Okay. So Y has extra rings up to time t. I'm going to couple one at a time for each extra ring. So for each I between 0 and nt is random, x superscript I will be the random walk that agrees with x, except that it has the first I of these additional rings. So x super 0 is x and x super n is y. From step 2, which I proved using step 1, I can couple xi and xi plus 1 such that every time after that extra ring, in particular at time t, the walk xi plus 1 is at least as far from the origin as xi is. And so if I put together all of these couplings, I get a coupling between x and y, where at time t, the walk y is at least as far from the origin as x.
Maybe Russell, I would like something a bit more explained as well, because you were stressing in the beginning the difference between monotonicity of, say, the speed and the question whether it can be coupled. You
Right.
sort of convinced us that there was not a coupling, but now
Right.
you're also using coupling. And
Okay.
so I'm sort of confused about coupling in which sense. So apparently the very nice couplings did not exist, but there are still some sort of, and this is where I'm sort of confused.
Sure.
What sort of couplings are possible and which are not?
Right. So what I proved was a coupling that has the property that for all times, the second walk is at least as far as the first is not possible. This does not have that property. This has the property that at time, if I only take a finite number of changes of the refresh ring up to time t, then at all times after time t, that property holds. The second walk is at least as far as the first. But there will continue to be new refresh rings. And so the coupling would have to start over again. Because remember what happened, this is a subtle point. The whole thing is subtle. So this step 2 said at all times after time t1. And how would we prove it? Up to time t1, they were independent, conditioned on this. We did not maintain anything about the distances between z2 and z1 up to time t, only after time, up to time t1, only after time t1.
So up to t1, it's a distributional statement, and afterwards it becomes an almost sure.
Correct. So we are forced to be tricky because the best coupling will not work. And so that's why, yeah, the whole thing is, yeah, I agree, it's subtle, but nevertheless, we can do it using coupling. Oh, I see I'm really virtually out of time. So Anyway.
You can take until 50, for example, let's say.
55, you said?
Until 50 or, yeah, 50, you can speak 5 more minutes.
Okay. So I remember I emphasized this reflection in the edge in a tree. Well, actually, that's one of the key ideas for trees. Is very simple. This theorem that I just proved extends to trees of all degree, but in fact, k-graphs of all Coccidir systems. And what is a Coccidir system? It's a group W with generators S defined by a certain presentation. What is the presentation? So for every pair of generators, it might be the same. I'm going to tell you a relation. I take S times S prime, raise it to the power M. That depends on SS prime, which is a positive integer or infinity. If S is equal to S prime, it's 1, which means S squared is the identity. So all generators are involutions, corresponds to a reflection. All the other integers are at least 2. If it's infinity, it means there's no such relation. So it turns out these are actually the orders of these elements in the group. And all of those examples, those reflection groups that I gave to you were examples. In fact, Coccidir groups are abstractions of reflection groups. Dihedral groups are one of the simplest examples, symmetries of a regular polygon. And the crucial property that Coccidir systems have, so we're considering k-graphs only with respect to these special generators, is the following. Suppose that W and WS are 2 adjacent vertices, and I multiply by this conjugate of S, WS, W inverse on the left. Left multiplication of a right k-graph is a graph automorphism, and in fact of the k diagram. Certain edges might be preserved, to call that M. And this map L interchanges the endpoints of each edge in M. We're going to call this set of edges a wall, also called a hyperplanar mirror. And it separates the vertices closer to W from those closer to the other endpoint, WS. Furthermore, if W is on, if the identity is on this same side as W, this assumption here, then for all V is closer to W on that side of the wall than to WS, if and only if it's also closer to the identity, then it's reflection across the wall. So on trees, walls are single edges. And in general, this map L, we say reflects in the wall. We could take, oh, actually, let me just illustrate. So here is this example of a nice K diagram. Here, say, is W and WS. The identity, say, is somewhere down here. And V is some other vertex, say, down here. The walls are these white geodesics. So this wall here, for example, you can see it contains edges of all generators in this particular case. And if I reflect on the wall, then I will go from a vertex which is closer to the identity and to W, then its reflection, and it'll be closer to the WS. So when I go from the identity to a place that's, well, so if I go from W, if I consider the first step, I want to show that it's more likely to be here than here. I do not have to cross this edge to get from here to here. I might go some other place. So instead, the same proof works when you consider the first time that you had a wall and that you might have a refresh ring. And then you reflect on the wall, and all the same proofs work. Exactly the same, other than that small change. Of course, you have to consider some algebra, a little bit of algebra, but then everything works. So now just quickly to sum up, what about the finite group case, distance to stationarity? This was Yiping's question. So stationary distribution is mass 1 over n if there are n vertices. Well, what do we mean by distance? Well, distance we could measure in various ways. For example, LP norm, or relative entropy. And so the first question to ask is, suppose you increase time, which is the same as multiplying all the generators by the same factor. Does that? And it does. You can prove this using majorization. So since I'm out of time, let me just not go through the details, but you can do that. And majorization implies if I do have that one distribution majorizes another, then there's a bunch of inequalities that you can get. And in particular, the LP distance of the first will be at least the LP distance of the second to the uniform. Same for relative entropy. You can prove that for abelian groups, increasing any generator. So first of all, for any time, you can check, I didn't allow you to read the definition, but you can check easily that you do get majorization if you increase time, and so distance goes down. For abelian groups, increasing rates individually also decreases distance. It turns out if you measure distance using p equals 2 or p equals infinity, then on any group, increasing any rates decreases distance to uniform. And for any finite Coccidir system, in any fixed time, increasing any rates always decreases the probability distribution at time t in the majorization order, and therefore in all these other particular instances. So the question, was always exist in Coccidir groups? Yes, for Coccidir systems, one given by the Coccidir generators. Well, if it's finite, there are finitely many walls. If it's an infinite group, there are infinitely many walls. But they're all similar to ones which include an edge with incident to the identity. So here's an example, S4 symmetric group, Katie, which is a Coccidir group, and this is this nice Katie graph. Anyway, if you change the generators, we may get surprising behavior that not the monotonicity we expect. I will concentrate on two examples: dihedral groups of order 87, not of order, on 87 things or on 41 things. So we said that at p equals 2, all groups have monotonicity and p equals infinity. We can get p arbitrarily close to 2, it appears, we don't have a proof, arbitrarily close to 2 on either side, and arbitrarily close to 4 on either side. But for some reason, we could not find any examples where we have a counterexample for p equals 4 or 6 or bigger. We have no idea why. So we don't know, we don't have a conjecture whether this is always true or whether it's just extremely hard to find because they're so rare. Even that would be interesting. Why would they be rare? So we don't know. And so I should end. Thanks very much for your attention.
Well, thank you. We can have a first round of applause. And okay, so are there questions?
Yes, maybe. Sorry, about the trajectory of the random walk on this Cayley graph. Can you say something about this trajectory? Like, how does it go to infinity? What are the typical trajectories that are followed?
So you're talking about the infinite transient case?
Yes.
Okay. So right. So there's structure known about. You're talking about the Coccidir case, I assume, or in general?
Well, or maybe just even on trees where you have the. Can you say something about the dependency, for example, between the rates and the trajectory followed by the random walk on this?
Okay, so well for a tree, because a tree is even if the rates are different, it looks the same everywhere. You're not going to see any difference of where it goes, unless you fix. You actually pay attention to labels. And then, of course, the ones with higher rates, since it's more likely to go there, it will. And of course, in that case, it'll be the same as discrete time, as long as you change the probability, keep the probabilities the same. You will go to those rays, it'll tend to go, it'll find some limiting ray, and it will go to those rays that are more likely, and they'll be, Hausdorff dimension, smaller Hausdorff dimension than the Hausdorff dimension of the full boundary. And you could get a formula in a sense. In fact, well, it's complicated. You're not going to have. It's going to be a solution to a system of equations, which you couldn't write down an explicit solution in general. But there are things known in trees. Trees are much simpler to analyze. Otherwise, of course, it depends heavily on the group. For a Coccidir system, it turns out you can decompose it as products of Coccidir systems, and the ones, irreducible ones, and if they're transient, they correspond to hyperbolic groups, which are similar to trees and similar to the examples that I was showing. Let me just make a very brief explanation. And so you can imagine there's, in fact, there's an abstract, somewhat abstract complex you can form for a general Coccidir group, and there'll be a boundary and it will tend to someplace on the boundary.
Thank you very much.
Yes, so I believe there is one question by Pierre Mathieu and one by Takis Konstantopoulos. I believe Pierre wrote first. So what about random environments? Yeah.
Coupled random weights with equivariant or not. Okay, so we actually asked that question in our paper. We do not know the answer. It's a great question. Seems like it ought to have a positive answer for Coccidir systems, but we don't know the answer.
Takis?
Just a clarification question about the Coccidir group. You said that for all S1 and S2, there is a power such that S1, S2 to the power is equal to identity. Right. That implies that I can also different powers for S2, S1, or what's happening if I?
That power that's given in the generator in the presentation is the order of S1 times S2.
Okay, and the order of S2 times S1? Same, okay.
Yeah. So just think about it, it's a polygon, right?
Aha.
Okay.
And that could be infinite, so I could have an infinite reflection group, like in 2 mirrors or something like that. Okay. The other question is, what kind of things can one learn by studying the random walks on Coccidir groups, about Coccidir groups? I mean, I guess people want to learn about Coccidir groups. Can you learn things by studying?
That's a good question. I'm not sure. I don't know of anything right now, but I'm not sure that there isn't anything.
Okay.
So, we certainly use this key fact I mentioned is key in the study of Coccidir groups. And that provides you with a lot of geometric information, and there's more. So, and of course we needed that to study for our results, but I don't know that, I don't have anything immediately to say on the other direction.
Okay, I mean, and here is a silly question. Could one tell that whether the group is finite or not by looking at the random walk? Maybe, I don't know, it's...
Well, in principle, it depends on how much time you give it.
Of course, you can simulate it and see.
But if, if you have if the Coccidir system, you have the presentation, you can tell everything about it.
I see. Okay.
If you're given a presentation, you can tell.
All right, but not for a general group. For Coccidir.
Everything. I mean, you can decompose it.
Okay.
Really pretty much what it looks like.
Yeah. Okay, thank you.
I think Jason's talk may give more information about that kind of question.
Thanks.
Good. And maybe I will have a last question, and then we will move to Jason's talk. But so thanks for the talk first. So yeah, there is this question about monotonicity on Kelly graphs. And in generality, there are some problems, but for Coccidir, we can handle some things. And I was wondering, in the transitive graph setting, so full transitive graph is too hard, but is it possible to make sense of the question and to get some theorems for certain transitive graphs that are not Coccidir groups? And in particular, I was thinking that when we have a Coccidir group, you mentioned the dual picture, and the dual picture naturally has also colors on the edges, but several blue edges popping off each vertex and so on. I was wondering if this graph could have some interesting features or not so much. I don't really know.
I'm not quite sure what you're saying. So the dual was this, right? Or this?
Yeah, in this picture, we have the right graph. And on the right graph, if we really want to assign them color in order to define rates, we could say that if I cross a blue edge, I'm blue. If if I cross a red one, I'm red, etc. But the resulting graph is not Kelly because from each vertex we can have several blue edges. Or
I see what you're saying. That's interesting. I never thought about that. Yeah, maybe you could say something in this case. I don't know.
No idea. Okay. Okay.
Of course, this is not a transitive graph, right? The graph on the white edges is not transitive, quasi-transitive.
It is quasi-transitive, right?
Yeah.
Quasi. Okay. Okay. So I don't know if there is something, but okay. Anyway, thanks a lot for all this nice math. Maybe a second round of applause, and then we will move to Jason's talk.